Okay, it's fine. Um, so I only I only have two goals today, which I can't imagine taking the whole time. But well, number one, to finish the discussion of spectral methods, and after that, in the notes comes a whole section on actually solving the systems that come up from elliptic PDE, like Laplace's equation, Poisson's equation that we've been using for examples. And that'll take a fair amount of time, and before we get into time-dependent problems later. Um, so, um, so I want to hold off on that newer stuff. So the other goal for today is, as much as possible, want to make sure that everyone's questions about homework 1 are put to bed. So that way, next week can be a combination of the newer stuff on elliptic equations and solving the linear systems that come from them. We'll look at, actually, it's kind of a 610 overview because we're going to look at direct methods, iterative methods, Credo subspace methods, but as a bonus for Haley, who's not here, multi-grid methods. Also, I want to use time next week to focus on whatever questions you're going to have about homework 2, which is on this spectral method stuff. So I think what I'll do is I'll use the first part of class to finish the stuff on spectral methods, and then we'll throw it open to whatever's still going on with homework 2. And I hope that the majority of you, because there was a particular part, I think it was 2B, that at least one of you who shall remain nameless decided not to do, and, well, announce it to everybody. And I hope that the majority of you do not choose that path, because that's what happens with these kind of problems, that these wrinkles come up, and it's a good experience to work around them. Okay. So continuing with spectral methods. Non-periodic. We have this differentiation matrix. D sub n that takes as input a vector u, and then so you multiply that and get this vector v, where ui is equal to value of some function u at the grid point xi. Xi is equal to cosine I pi over n. So we have an I goes from n. So all the xi's are in the interval -1 to 1, including the boundary points. And then the output, vi, is an approximation of u prime at the same point. And this is with spectral accuracy. Order h to the capital N. So the more grid points you use, not only is it more accurate, which you would expect, but also the order of accuracy keeps improving. All right. Provided that the function itself, and you're taking a derivative of, is infinitely smooth, which happens with PDEs of interest like Laplace's equation, heat equation, etc. Okay. So what I want to focus on now is, because yesterday was about how do we construct this matrix, and they gave me painful formulas for the entries of Dn. But we can also carry out matrix vector multiplication with Dn. That's procedure I described at the end of yesterday, where you perform an even extension of U, and you perform a FFT on that. You differentiate with respect to, I'll call this theta I. So we differentiate with respect to theta, and then just use a chain rule to correct that to get the derivative with respect to x. And that is a faster procedure. So at least we have a way of performing matrix vector multiplication that's efficient. Okay. So you look at some examples of how we use this matrix to solve PDEs with spectral accuracy. Okay. So our first example we have is BVP boundary value problem, Poisson's equation. So UXX is equal to e to 4x on minus 1 to 1. And then we have homogeneous Dirichlet boundary conditions. So U is equal to 0 at plus or minus 1. So how we solve this numerically, and yeah, I know we can solve this analytically, but this is just an example from a method. You solve dn tilde squared u is equal to f, where in this case, u consists of the solution values only at the interior points. We remove the boundary points u0 and un at plus or minus 1. The vector f, similar, it's the right-hand side function, evaluated only at the interior points. Okay. And then dn tilde, as opposed to dn, this is dn with the first and last columns removed. So instead of this n plus 1 by n plus 1 matrix dn, we have n minus 1 by n minus 1 matrix dn tilde. And it's squared because of we have second derivative. And dn is used to compute just the first derivative. And it's because the boundary values are 0 that we can just go ahead and drop those first and last rows and columns. If it was non-homogeneous Dirichlet boundary conditions, we could still drop the first and last rows because we know what the we don't need those equations, we know what the boundary values are. But as far as the first and last columns, we would need to move those columns times the boundary values over to the other side, like we've seen in other examples. So you'd have to do some boundary term correction, but then you would still solve the same system just with a modified right-hand side. So not much to do here. As far as how we solve this system, now if you were to just go ahead and solve this directly, like using a direct method, unfortunately you'd be expending order n cubed operations because dn is a full matrix. Pretty much, actually, yeah, all the entries are non-zero. What I would recommend for this is perhaps using an iterative method that would require only matrix vector multiplication. Because matrix vector multiplication of dn or dn tilde is efficient, we can use the FFT. And some of the methods I'll talk about next week, like Krylov subspace methods, would be good for that. And yes, just plain Krylov subspace methods, not my own Krylov subspace spectral methods. So, try not to mention these in this class yet. Okay. So any questions about the setup here? Okay. So now what I'm going to do is, for my next example, I'm going to change the problem to make it more interesting. Because when the PDE is linear and time independent, you can just set up a system of linear equations and then solve by whatever means. But what if the PDE is nonlinear? So now I have uxx is equal to e to the u on minus 101. Still Dirichlet boundary conditions. So what we can do here is use an iteration. So same matrix as before, dn tilde squared. uk plus 1 is equal to e to the uk. So what you can do is we can choose u0, and actually what I would recommend for this is just go ahead and choose u0 to be the 0 vector. Reason for that is at least it satisfies the boundary conditions. So you can substitute that into here, get your right-hand side, and then you and then you solve the system. Whatever you get as a solution, you substitute back into the exponential, get a new right-hand side, solve the system again, keep going, and hopefully it'll converge. So another way of writing this is each new iterate is equal to dn tilde squared inverse times the exponential of the previous iterate. Now, what kind of iteration is this? What do we call this?
Is it like a fixed point?
Yes, it is a fixed point iteration. Now, the interesting question would be, would this fixed point iteration converge? And honestly, that's kind of debatable. Because as far as it would depend on the eigenvalues of dn tilde. I mean, you're raising them to the minus 2 power. And normally, I don't really have good knowledge of the eigenvalues for the Chebyshev differentiation matrix, but like for finite difference, for instance, you have eigenvalues that get pretty close to 0 and then go up to infinity. You take 1 over those, and some of those eigenvalues can get pretty large. So this iteration might need to be modified in some way. Like, for instance, maybe do some sort of splitting, which I'll talk about next week when we get to iterative methods. That if you break this up into a sum of 2 matrices, you leave one term here and you move the other term over here, then that can you can get some effective iterative methods that way. And that's how you get methods like Jacobi, Gauss-Seidel, SOR that were covered in 610 that we're going to revisit next week. Another possibility is to use You could use other iterative methods, like, well, Newton's method would kind of be difficult because you'd have to, well, yes, you needed like well, yeah, you need a Jacobian of that, which it can be done. Um, it's definitely not easy. Um, so you could, or an approximation of Newton's method, like a secant-like iteration. Um, so there are other options here. The point is, you can't solve this equation. You definitely can't solve exactly. So you need to use some sort of iterative method in conjunction with dn tilde squared to solve this P. Well, that might be kind of fun to try in MATLAB. We form the MATLAB differentiation, the Chebyshev differentiation matrix using those nasty formulas. Okay, this is not something we could easily try right here in class, because coding up that matrix. But then once you have a matrix, then it wouldn't be too difficult to try this iteration out and see if it converges. So if I had a dull moment, then I would actually go ahead and do it. Okay. Another example is uxx is equal to lambda u, where lambda is a scalar, unknown. Again, a minus 1 to 1. Same homogeneous Dirichlet boundary conditions. So this is an eigenvalue problem. And with the homogeneous Dirichlet boundary conditions, you can approximate this by a ordinary matrix eigenvalue problem, dn tilde squared u is equal to lambda u. So then what you can do is solve this in MATLAB, use the function I. So you can do so that lets A be dn tilde. Then I can use the I function on A. Now, they would point out my mistake. Yeah, I think it would be squared. Now, by doing this, I will get the wrong eigenvalues. Now, D is a diagonal matrix of the eigenvalues of A. I want D squared, but I can just go ahead and square them. But the eigenvectors that I get are also the eigenvectors of dn tilde squared. So I can either go ahead and form dn tilde squared and feed that in here and get my answer directly, or I can just feed that in and just have to remember to square the eigenvalues afterwards. Really just squaring the diagonal elements. So mathematically doesn't matter, but from a practical standpoint, one reason why I would take this route is I have formulas for the entries of dn tilde. I do not have formulas, might be able to look them up, but I don't have them in any of my sources, for the entries of dn tilde squared. And I definitely don't want to perform matrix multiplication to get dn tilde squared to put it in here. No. Because that's an order n cubed expense. And I'm going to incur enough expense just doing this. so this can save a little effort. Keep in mind that if you have that the eigenvectors of any function of a matrix are the same as the eigenvectors of the original, and that if you have a function of a matrix like squaring, you get the eigenvalues, you can apply that function to the eigenvalues. Okay. Now, another option that's worth mentioning, especially when we use a large number of grid points, once n starts getting to be like in the thousands, this command can actually take a pretty long time, especially since dn tilde is a full matrix, all the entries non-zero. Actually, yeah, we've seen that using those kind of functions on large matrices. It just gets out of hand. So another option might be use eigs, which has a similar usage, like the same, you get the same kind of outputs from it. But what that does, eigs as opposed to eig, to get selected eigenvalues. For PDEs, you're normally interested in the smallest eigenvalues in absolute value.
Why is that?
Because, well, for example, suppose you're solving a time-dependent PDE, like a UT equals a heat equation, so UT to U of X. You're taking exponentials of like negative eigenvalues times t, and with larger eigenvalues, your decay is so rapid that those terms will be negligible. Also, if you're solving, instead of a time-dependent problem, solving Poisson's equation, you're inverting, so your dominant terms will come from 1 over the smallest eigenvalues to get the largest terms. So you can use eigs and you can tell it how many eigenvalues you want. And do you want the smallest or the largest? And so it uses iterative methods, like preload subspace methods, to compute those selected eigenvalues a whole lot faster than this would. If you have if your matrix, this matrix is not sparse, but if you had a sparse matrix, like a finite difference matrix, you could not use, you can't use eig on a sparse matrix. You have to convert it to a full matrix first. But eigs can be used on either kind.
You can't use eig, but you can use eigs.
Right. Yeah. So what you would get by using eigs, so once you get your output, each column is a vector u containing a solution of this PDE for a given eigenvalue that's on the diagonal of D. And because we're working with dn tilde, where we chop off the first and last rows and columns, your solution that you get as a column of x is it's evaluated only at the interior points, and you know the boundary values are 0. So any questions about that one? Okay. Let's look at some 2D ones. All right, so now I have a Poisson's equation on a rectangle. Uxx plus yy equal to some function f. So the domain is the square minus 1 to 1 squared. And then homogeneous differential boundary conditions. U is equal to 0 on the boundary. Okay. I have a strange choice of function here, but whatever. Well, for this discussion, it doesn't really matter what f is. As long as, as long as it is zero mean, a solution exists. Okay. So we solve this system equations. Ln u is equal to f, where vectors u and f are take the values of u and f only at the interior points. We're not dealing with boundaries, since we know u is 0 on the boundary. Where the matrix Ln comes from taking identity matrix Kronecker product with dn tilde squared from previous examples, and then we go the other way. Now, I think you actually have Kronecker product described in later notes, but the way the Kronecker product works is so we have two matrices A and B, and A is M by N, and B is P by Q. Then the matrix that you get, you multiply the sizes together. So this result is MP rows and Q columns. And what you do is you take B and you tile the result with B. But within each tile, you multiply B by one of the entries of A. So this would be A11B, A12B, A1NB, and AM1 down to AMN. So tile with the second, multiply each tile by the entries of the first. So what that would mean is the first term, identity d tilde squared would just take the matrix dn tilde squared and repeat it all along the diagonal, because I has ones along the diagonal and zeros everywhere else. Whereas the other matrix, dn tilde squared Kronecker product identity, would have like d11 identity, d12 identity, well, dn tilde is n minus 1 by n minus 1, and so on. Okay. Now, one of these matrices, like one of these terms, this term or this term, one of them is for partial derivative, second partial derivative with respect to x. The other is for second partial derivative with respect to y. Now, as far as which is which, that depends on how you choose to order your grid points within this vector. Like, for instance, do you order them with, so two logical possibilities are x1, y1, x1, y2, x1, y3, and so on. Like the x stays the same, and you repeat and you iterate through the y's until you get to the end, and then you get x2, 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 and so forth. Or the other way around: x1, y1, x2, y1, x3, y1, and so on. So this term, it's acting on points that are right next to each other in this vector for purposes of differentiation. So what that means is, if I am using this ordering, where the y's are changing from one element to the next, then this is second partial with respect to y for this ordering. If I chose the other ordering, then that matrix is second partial derivative with respect to x.
What is the ordering for?
Well, because what happens is you're solving a 2D problem.
It's for your right-hand side.
Well, actually, both a solution and a right-hand side. Any vector that is meant to represent a function of x and y is still going to be a vector, not a matrix. Even if that's because you're going to 2D. So you have to have some way of consistently ordering the points. When I get into linear systems next week, we'll talk about other possible orderings from a standpoint of what is best for solving the system. But just to get the ball rolling and studying discretization, once you have a second derivative matrix in one dimension, it's very easy to go from 2D to 3D by using these Kronecker product operations. Each one gives you one term of a Laplacian. Which one depends on the ordering. When I see what the Laplacian is, doesn't matter what the ordering is, the matrix setup is the same. You still do those two Kronecker products. It's a matter of which differentiation operator does each term refer to. I should mention there's a reason why I'm going to label this as a preferred ordering. And here's why. So I'll use like a code snippet to illustrate my point. So let's suppose we have really to evaluate a given function f of x, y on the grid in order to get a vector f. So basically, for instance, suppose I'm given a function f for previous example, and I want to form my right-hand side. So if I make my vectors for x and y, so given vector x, which consists of my interior grid points, and then similar for y. Okay, so I have those vectors in MATLAB. Then how I would proceed, and then also given function handle, so if I've gone ahead and typed that in, so I have a function handle f that I can use to evaluate f at any point x, y. Then here's what I can do. I can say x2, y2 is equal to mesh grid, and I pass in the vectors x and y. And what that outputs are x2 and y2 are matrices that give you the x and y coordinates, respectively, of all the points on your grid. So I can describe what's in these matrices. So x2 would have x1 all down the first column, x2 down the second column, and so forth. And then y2 has the corresponding y coordinates. So that would be y1, y2, yn minus 1. And then that's repeated. So here we have x1, y1, x2, y1, and so forth. So if you kind of like to overlay those, you'd have all the possible combinations. You'd have all the grid points. So then what I could do is to make my vector f, I could I'll make this variable called fmat for f matrix. That would be I could plug these in to f, assuming I've defined my function handle in a way that is vectorized. Like, for instance, I'm using dot multiplies or dot exponents where needed, so that I could go ahead and plug a matrix into f and have it work as intended. So what that gives me is f of x1, y1, f of x2, y1, and so on. F of xn minus 1, y1, and then f of x1, y2, and so on. So however these are ordered within these matrices, those points are plugged into f. So now I have my f values, but I don't want a matrix, I want a vector. Well, what MATLAB command would I use to get a vector out of that? Yeah, reshape. So I could say f vector equals reshape f mat, and then the size would be, the size is n minus 1 squared rows of one column, or I wouldn't have to do that. I can always do num_l, number of elements in fmat. So don't have to bother figuring that out. This is because reshape just takes the existing elements and puts them into a different kind of array. It's really just a bookkeeping exercise, so it's very cheap, thankfully. But then the thing is, how does reshape work? It goes column by column. So it'll start by taking all the elements in the first column, then moving to the second column, and that is in keeping with this ordering. So that's why I say that ordering is preferred, because it works well with how MATLAB's functions work, at mesh grid and reshape and all that. Whereas if reshape worked across rows, then it'd be a different story. This actually has to do with how different programming languages work in terms of matrix storage. That if you have a two-dimensional array in whatever programming language, then how are the entries of that matrix, a two-dimensional array, laid out in memory? Does it go across rows, row major order, or does it go for the columns, column major order? Fortran is column major ordering, and the lowest level functions in MATLAB are implemented in Fortran. C, C++ are row major. Not sure why the difference, but.
Yeah, how do you find these kinds of, rules or whatever?
I found it by experimenting. Like what I've meant.
I just suppose that if you want to help them, where they really include just opposing method type help what?
Uh,
You get,
well, sometimes help on the individual function can give you an idea, and I've definitely used that for a lot of these functions. One thing I never looked up was how FFT behaves. In what order does it return the frequency components? I just kind of figured it out by trying certain simple cases and seeing how it did. Now, I'm sure I could have looked that up somewhere, but I've actually learned a lot more about this just by trying things. I would examine these matrices that MeshGrid produces and see, oh, okay, this has the same elements throughout the first column. And yeah, so yeah, so everything I've told you is based on my playing around. All right. Okay. Well, that's a helpful little side there. Okay. Now, last example to build off the previous one. Another 2D problem. Yes, so that operation, I don't know if no, I didn't write it down. Kronecker product. Now, so for this example, we have wave equation. With the source term. So minus VTT plus VXX plus VYY is equal to e to the IKT f of xy. And we'll assume like the same spatial domain as usual. Normally the wave equation is written the opposite way, VTT minus Laplacian, but that just, so it's more convenient to write it this way, because you would just negate the right-hand side. So what we do is, we don't actually solve this as a time-dependent problem. We don't have to. So what this is doing is it's taking an fxy and giving it a frequency in time, so there's oscillation in time. But what we do is just attack this problem. We assume the solution has a certain form. V of xyt is equal to e to the IKT u of xy. So if I go ahead and substitute that throughout, then the second derivative of this with respect to time is only going to focus on this part. That part's independent of time. So we get minus and then ik squared e to the IKT u of xy from the VTT term. And then when I differentiate this with respect to x and y, it only affects this part, not this one. So I have plus e to the IKT uxx plus uyy is equal to e to the IKT f. And now I can just go ahead and cancel the e to the IKTs that appear in every term. And this is why I wrote this with a strange sign convention, because ik quantity squared is minus k squared, and then it gets negated again to give a plus. So now I have uxx plus uyy plus k squared u is equal to f. So this time-dependent PDE has been reduced to a time-independent PDE, and not a kind that we've seen before, or I might have brought it up once, but not really, no detail. This is called the Helmholtz equation. So this comes up a lot in seismics, where you start a wave equation, but then you reduce it to this Helmholtz equation. This can be a pain to solve because Laplacian has negative eigenvalues, but here we have a term of positive eigenvalues. So we can get, depending on the value of k, we can get both positive and negative eigenvalues. This differential operator is therefore called indefinite. And that can pose some problems for iterative methods. Solving Helmholtz equation causes some problems for KSS methods too, I might add.
I have a question. I mean, this question comes to my mind that if it was this equation was modeled to have to be time dependent based on the reason, right?
Yeah.
And then when we kind of make a non-time dependent equation, it's like I know that it will help you to solve it, but you're gonna kind of lose one of those important, factors, which was time. So is there any other way to kind of switch to the previous one? Just because based on the way that they modeled that.
Well, okay, well, first couple things. Once you solve this, you still have your time-dependent solution because you just multiply by a to the I kt. But the other thing is, generally what's done is whatever source term is most likely approximated by this. Like if there's a particular dominant frequency in time, then they just use that, which allows this transformation to be made. Because if this was a more complicated function of t, you couldn't do this. Now, is that simplification justified? It's never matter, because you might call it laziness, if you will, that they still want to solve time-dependent problems, so they simplify this maybe excessively to solve it this way. But if you can't do that, you always can go ahead and just try solving this directly using the methods that I'm going to cover. Like, for instance, Maxwell's equations. People treat Maxwell's equations by making a change of variables to make it time independent. But you saw one of my papers how I just went ahead and did the time dependent problem. A number of people have too. So it's a choice. But yeah, you really shouldn't do this unless that really is your source term, that you're not just cutting corners. Okay, so to solve this, you can use a similar approach as in the other examples. You can solve a system ln squared plus k squared identity u is equal to f, where the vector f is built actually using a procedure I described in the previous board, and then u is your solution with the points ordered in the same way, and then you could, like for instance, once you solve a system, you could reshape u into a matrix for like plotting purposes. You can pass it to surf and plot your solution that way.
Should it be ln squared?
No. Yeah, so ln is the matrix for the Laplacian. But yeah, it uses dn tilde squared. So the thing is, this is, yes, so from a numerical linear algebra point of view, this problem is more difficult than the previous one, because ln by itself is a matrix that is negative definite, so you can just negate it, and it's positive definite. You can use Cholesky or conjugate gradient or something like that. Whereas here, this matrix is indefinite. So you could try using, it's still symmetric, so you could use like LDLT, or you can't use conjugate gradient, but you could use like SymLQ for symmetric indefinite systems. I'll talk more about this next week, but But the fact that you have positive and negative eigenvalues is a complication. Okay. Any questions about this one? So I've come to the end of the notes, and this is a logical time for a break anyway. So I'm going to, so I can show myself in my office for a little bit and have lunch real quick, and then I'll come back and see how you guys are doing with the homework, or I can also, there might be no time for any other questions you have this morning, Eva. So we'll figure out what you need from a other hour.